Let us now see the experiment called spectrometer grating. The aim of this experiment is to determine the different wavelengths present in the light emitted by a mercury vapor lamp. The apparatus that are required here are the spectrometer, mercury vapor lamp, grating with 15,000 lines per inch or approximately 6 lakhs lines per meter, spirit level, a magnifying lens. A grating stand to be mounted on the table, prism table. The formula used here is, during normal incident, the wavelength of light lambda is equal to sin theta by capital N into small n in meters. The explanation of the symbols are: theta is angle of diffraction in degrees, capital N is number of rulings per meter made on the grating, which is in lines per meter, small n is the order of diffraction, it has no units. We will be basically dealing only with first order diffraction, so in our formula small n will be 1, and lambda is the wavelength of light, that is the mercury vapor lamp what we are going to use in the experiment, and find out the wavelength of different colors in it. So the unit for that is going to be meters. Let us now see the procedure for finding the wavelength. As we have seen already in the formula, the grating plane has to be arranged normal to the direction of incidence. Only then our formula is valid. So the first thing we have to do after the initial adjustment is adjust the spectrometer for receiving the rays which are normal to the grating plane. But before we start, as usual, we do all the initial adjustments, that is, loosen the telescope screw, adjust the telescope for focusing a very distant object, then see through the collimator, open the shutter and keep a very small slit, and then bring the telescope in line with the collimator, and then use the fine adjustment this side and make a very sharp slit. Then of course the next one is tighten the telescope main screw and coincide the vertical cross wire in the telescope with the image of the slit. After doing this, we can make this direct reading 00 and 0180. Now we have coincided the direct reading with the vertical cross wire, and the direct reading has been adjusted by loosening the vernier table main screw and approximately adjusting first for 180, tightening the main screw of the vernier, then using the fine adjustment of the vernier table, we have coincided the direct reading to be 00 on one side and 180 on the other side. Now our next procedure is to adjust the grating for normal incidence. So you can see here, this is the collimator, and now actually we have the telescope position here. Now we have coincided the direct reading to be 00 180. For adjusting for normal incidence technically, what we do is we place the telescope at 90 degrees. That is, we have 00 as one of the direct readings now. So loosen the telescope main screw, rotate it freely and keep it in a position so that it reads 90 degrees. Now it means that the angle between the incident ray which falls on the grating, which we are going to mount shortly on the grating table, and the reflected ray from the grating which reaches the telescope is 90. That is, the angle between the incident and the reflected rays is going to be 90 degrees. So if we draw a normal to the grating plane, you will find the angle of incidence would be 45 degrees and angle of reflection is also 45 degrees. That is why we get angle between incident and reflected rays as 90 degrees. At this stage, what we have to do is to make this grating normal to the line of incidence. You have to rotate the grating table by another 45 in this direction. Then what will happen? The angle between the incident ray and the grating plane will become 90. And what does that mean? It means that the grating plane is normal to the line of incidence of the ray. So that is what is shown in the next diagram. You can see the collimator and then the rays coming from the collimator falling normally on the grating, and so this is that line, and you can see on both sides the grating disperses the white light into different colors, and hence we will be making measurements on the angles. Let us see how to do this now practically. We loosen the telescope main screw and keep it so that the vernier reads 90 degrees. Don't bother about the other side of the vernier. See the 0 side and keep it at 90 0. First tighten the main screw, then using the lens see if it is at exact 90. Now we have placed the telescope correctly at 90. You can also see the reading now, whether it is at 90 on that vernier. Now you can see the reading now is 90 there. 90 on the main scale coincides with the 0 of the vernier. So we have the desired position of the telescope. Again, ensure whether the main screw is tight so that the telescope should not move from the position. We have now leveled the prism table also and fixed the grating stand perfectly so that its plane exactly bisects the table. Fix it so that it exactly bisects the table, and also have the table to be tightly fixed. You can still rotate it. You can see that. Don't leave it loose like this. You have to keep the prism table fixed tightly, and so that you don't get a very free movement. So next what we do is take the grating out, handle the grating very carefully and place the grating like this so that its plane is bisecting the prism table. Now hold the vernier table with one hand as usual and rotate the prism table alone so that the reflected ray is seen through the telescope. Rotate the prism table until you are able to see the reflected ray, that is the same type what you see as the direct reading into the telescope. When you see that coincide the white slit with the cross wire, at that stage stop rotation of the prism table. At this stage the angle of incidence is 45 degrees on the grating plane. Now we have coincided the vertical cross wire with the image. As I have told you earlier, the next thing we have to do is we have to rotate the grating by another 45 degrees in this direction, which means here it is 90. So it should be either 90 minus 45 or 90 plus 45. That can be ensured when you rotate. So I am now, you can see my hand, I loosen the vernier table, because when I loosen the vernier table, along with the vernier table, the prism table also will rotate. So you can see my hands, I have loosened the vernier table and keeping an eye on the reading which is at 90, I rotate. Now it is actually decreasing, so I have to now coincide at 45. So 90 minus 45 is 45. I rotate, you can see the grating plane also is rotating in the desired direction now. So as I told you, clockwise is what is increasing. So now keep it at the approximate position, tighten your vernier table, and using the fine adjustment which is on your side, using the lens exactly coincided at 45 so that you get the correct position. Now the reading is 45 on this, and you can also see that the grating plane is normal to the direction of incidence. Just by one look you can say whether you have done it correctly, whether it is normal to the direction of incidence. You can see now that we have coincided the 45th reading. Stop on. You can now see that we have coincided 45 degree mark, so that the grating plane becomes normal to the direction of incidence. Now we have adjusted the spectrometer for normal incidence. That is, we have made the grating plane normal to the direction of incidence. We release the telescope now to obtain the spectrum. This is the direct ray, and first from the direct ray you would see violet 1 and violet 2 if it is perfect, and then blue, green, yellow 1, yellow 2, red on the right. Similarly in the left, it is towards the left from the direct reading we will obtain violet 1 and 2, blue, green, yellow 1, yellow 2, and then red. You may also get red 1, red 2, red 3, etc. You can record the extreme red for calculation. Let us see how we are going to bring the telescope for recording the readings. Loosen the telescope screw and then release it and see whether you are able to get the direct reading. You also ensure before doing this the vernier screw is tight, because otherwise everything will start moving together. So once you see the direct reading, you can move the telescope towards the left and towards the right, and you will be able to see all the colors what I already showed you now. So first what you do is go either to the extreme left or to the extreme right, coincide the extreme red first order almost with the cross wire, then tighten the telescope screw, main screw, use the fine adjustment and exactly coincide the extreme red, and then take down the reading for this. As earlier stated, the setting of the telescope is such that for one setting you will get two readings, that is vernier A and vernier B. That is for the extreme red you have to record both, vernier A and vernier B. Once you have recorded this in the tabular column provided to you already in the appropriate place, which I will be showing you shortly, move the fine adjustment so that it coincides with yellow 2, because the second away from direct reading you will get yellow 2. Coincided, take the reading again, two readings, vernier A and vernier B, then coincide with yellow 1, which will be very close to LO2, it will be like one line split into two. So the difference between LO1 and LO2 readings will be of the order of a few minutes only. When you are doing the experiment, ensure that the readings are okay when you are doing LO1 and LO2. Next, move to green, and when you are doing green, note the green reading in the tabulation where you have to find out number of lines. You can assume the value of the green wavelength and then calculate the number of lines in the grating and use this number of lines for calculation of the other wavelengths. You don't need to do this separately. As you are doing the experiment, record the green reading in the column provided for the number of lines in the grating. Slowly proceed to blue and violet. If you are unable to move, loosen the main screw, use the violet, tighten it, then use the fine adjustment. Once you have completed all the first order readings on the right hand side, that is up to violet, loosen it, that is loosen the main screw, and then go to the other side, that is the left side, and start there from the violet and go towards the extreme red, recording 2 vernier readings for one setting of the telescope. The experiment would be complete. We have to record the readings in the following table. First, fill the least count, which is 1 minute. Number of lines per meter in the grating N is to be found from the value of green. So leave it now for the moment. Order of diffraction is 1. So we have the name of the color here. We have red 2 and red 1 also. Sometimes red 3 also is seen. Don't worry, whatever is given you record it. So we start with red 2, either from right or from left. So the diffracted ray reading when telescope is in the left for red 2, that is VA and VB, vernier A and vernier B, we will be recording here and here. So first we will be completing all the left readings then. So then come to red 1, then orange if it is visible, then LO2, LO1, green. Write the green value here when you are recording, but later on we will transfer this reading into the other table which I am going to show you. Then bluish green, blue and violet. So you have completed the readings on the left. Now start going to the right. So we will be starting with violet. So you will be reading the readings like U. So record the violet readings here, then bluish green, then green, LO1, LO2, orange, red 1 and red 2. This is how you will be taking the readings. Now I told you where you should go and write the green readings. This is the table for finding out N, that is number of lines in the grating. Fill the least count for spectrometer, which I have already mentioned to you in the earlier experiment. The least count of the spectrometer is 1 minute. Wavelength of mercury green lambda G is assumed as 5461 into 10 to the power of minus 10 meters. Order of diffraction is 1. We don't need to worry about second order. Whatever readings you had in the other tabulation, transfer that green readings into this, that is VA, VB, and for the right it is VA prime and VB prime. And we can calculate the number of lines from this data. I will show you a sample set of readings. You may not get exactly the same values, but we will use that sample set and find out number of lines in the grating. This number of lines slightly varies from grating to grating. So when you do it in class, you may not get exactly the same value. We will now take a sample reading. We can see the reading on the left is for green 295 degrees 30 minutes, 115 degrees 15 minutes. And VA prime, that is the right reading. When the telescope is in the right hand side of the direct reading, We have VA prime as 334 degrees and VB prime as 153 degrees 50 minutes. We will now see how we can calculate angle between the diffracted rays, that is 2 theta. We can see this reading on the right is 334 degrees and here it is 295 degrees. We need to find the difference between VA and VA prime, that is VA difference, VA prime. You can see how the calculation is done. 334 degrees and then you have 295 degrees 30 minutes as earlier indicated. Borrow 1 degree from here, which becomes 60 minutes. So this becomes 3. So 60 minutes minus 30 minutes is 30 minutes. 13 minus 5 becomes 8. And 12 minus 9 becomes 3. So we have 38 degrees 30 minutes as 2 theta for VA difference, VA prime. Don't use the calculator for doing this. Do it manually. Similarly, the difference between VB and VB prime is 153 minus 115. So we have 38 degrees 35 minutes, which is what is written here. What we need is not 2 theta but theta, the angle of diffraction. So that is going to be this divided by 2 plus this divided by 2 again divided by 2. Instead we can simply do x plus y divided by 4 and that is what is given as 19 degrees 16 minutes. When we are doing VA difference VA prime and VB difference VB prime, what are we calculating? The angle between this setting of the telescope and this setting of the telescope. And what is the angle of diffraction actually here? This is the direct ray and this is the diffracted ray when the telescope is at the left. So this angle is theta, this angle is also theta. So the whole difference is 2 theta. So that is what we are calculating as VA difference VA prime or VB difference VB prime. So to find theta, we are doing x plus y divided by 4, which is what we calculated now as 19 degrees 16 minutes. Now we can calculate n as sin theta by small n into lambda of green. So we have sin 19 degrees 16 minutes divided by order of diffraction is 1 into 5461 into 10 power minus 10, and the number of lines can be calculated as equal to 604347 lines per meter. Using this now we can calculate lambda for different colors. Let us now see a sample set of readings for calculation of the wavelengths. You can see all the readings are tabulated as follows. Up to this is what we are going to record. This side of it is the calculated values. So we have for red 2, red 1, orange, all the colors. We have the readings for VA and VB on the left and VA prime and VB prime on the right. We will simply take LO2 and LO1 as example. So LO2 you can see 294.20 and 114 degrees 5 minutes for the left hand side, and 335 degrees 15 minutes for the left and 155 degrees on the right. So 2 theta is calculated as 40 degrees 55 minutes for left as well as right, which means angle of diffraction as shown earlier is 20 degrees 27 minutes. So there we calculated n. Now we calculate lambda by substituting the value of n. What we have calculated, you can see the n value is written down now as 604347 lines per meter and order of diffraction is 1. So similar way in which we calculated n, we calculate lambda now for LO2 by substituting the n value, and that is obtained as, in this case for LO2, 5783 into 10 power minus 10 meters. Similarly for LO1 you can see the reading is Now for theta, that is the angle of diffraction, 20 degrees 17 minutes, which gives a lambda value of 5738.41. Note the reading for LO2 and LO1 differs only by 10 minutes in this case. It may not even differ by 10 minutes in some cases, it will be lesser than that. However, it should not exceed 10 minutes. And the lambda differs only by, here you can see it is 5783, here it is 5738, maximum 5 nanometers. It only differs by 5 nanometers. In a similar fashion, all the colors lambdas can be calculated. Also note that starting from red to violet, the angle of diffraction will keep reducing. Also have a track on that, because we are moving from right end to the direct reading, so slowly the angle of diffraction decreases. So we should also keep a track of that.